so other people can rewatch it later on. All right. So first of all, I want to thank everybody for joining us today, and I want to thank you, Paul, for being our guest today. And I think the best thing is if you can start and introduce yourself and tell us what you do with ColdQuanta and how you got there, maybe some background.
Yeah, sure. Happy to do that. It's a bit of a long, unwinding story, but I'll try to keep it short. So I'm Paul Lipman. I'm president of Quantum Information Platforms at ColdQuanta. I also, like you, went to business school on the other coast at Stanford. So I started out in the UK. I was a physics major many years ago and worked in consulting like many prior to business school. And then after the GSB, I spent the best part of 30 years in the internet and software, and the last decade or so as the CEO of a number of cyber security startups. I'd always been interested in physics since my undergrad days, and when IBM launched the first cloud-based quantum computers, and this was, I think, in 2016, and maybe a couple of years later, I started to, just out of personal interest, learn to program the ones that they made available for free, and was learning about quantum. And when I sold my last company, I was helping one of my investors to diligence some quantum deals. And through that, got introduced to ColdQuanta. Was not intending to do a full-time gig again for some time, but it was really too good an opportunity to pass up to actually come into a quantum organization and take an executive leadership position. And this is an industry, kind of notwithstanding, maybe some of you would have seen the kind of recent issues one of the public companies has faced with a very aggressive short seller putting out very negative press over the last couple of days. Notwithstanding that, this is just an absolutely fascinating industry, intellectually fascinating, and an industry that I think is poised for very rapid growth. So that's a little bit about my background, how I came to ColdQuanta. I've been here for just over a year.
Wonderful. And I did a check, and ColdQuanta is located at Boulder, Colorado, which for this type of a company, for emerging technology, it's not the type of place you imagine you would find a company, right? So how come? What's so special about Boulder, Colorado?
Yeah, so I live in the Bay Area, but I split my time between the Bay Area and Boulder. And interesting, the Bay Area, I forget the stats from when I was at the GSB, but some kind of huge percentage of people, once you spend a couple of years in Northern California, it's kind of hard to leave. So Boulder, interestingly, is actually a hotbed of quantum technology. And there's probably, I would say, in the US, maybe kind of three main real areas of kind of innovation, startup activity, and academic activity in quantum. So Boulder is one of them. Certainly the MIT, Harvard area is another, and then Chicago is a third. And Boulder has one of the leading physics research departments, also is home to NIST, the National Institute of Standards and Technology, and then JILA, which is a lab that is a kind of a JV between the two. And a lot of the really leading work, certainly in atomic physics, is done here in Boulder, Colorado. And actually, and I'll talk a bit about this later, you're probably familiar with the forms of matter, a solid, a gas, a liquid, and maybe you're familiar with plasma. There's also a fifth form of matter called Bose-Einstein condensate, which is where you cool atoms down really, really close to absolute zero, and they stop acting as atoms, and they act as a kind of a single quantum object. And that was a theoretical idea, and that Bose-Einstein condensate was first created here in Boulder, Colorado, and our co-founder was part of the team that did that. And then as he started to think about practical applications, decided to start a company, and that was the birth of ColdQuanta. But there are other quantum companies certainly in the area, and kind of the whole supply chain, everything from lasers to quantum components to full stack quantum companies like ours here in the kind of the Boulder and surrounding areas.
So what you're actually saying is that it's kind of an evolution of past research that started at Boulder University, and this is one application that you found, and basically like cold atoms were born out of this discovery or ability to cool atoms that
Exactly.
cold. Right?
Exactly. And the real core of what we do, I'll actually show you one of these products. So we really lead the world in designing and manufacturing. And what I'm holding up is a glass cell that is actually the heart of our quantum computer. So we trap atoms, in our case, cesium atoms and sometimes rubidium atoms in that glass cell. We then cool them down using lasers. So there's no cryogenics. You may have seen these pictures of kind of the IBM refrigerators. We're just using lasers to cool the atoms. And kind of maybe the simple way to describe it is heat is motion, right? So if you're sitting in a room right now, the atoms in the air around you, the molecules, are bouncing around at roughly 1,000 miles an hour. And that's the heat. It's the motion of the molecules. Well, if you can slow the molecules down, you're taking away the heat. And we do that with lasers. And we cool them in that cell for the quantum computer to about a few millionths of a degree above absolute zero. We have another system, which is actually available online. I can put the URL in the chat. And there you can create this Bose-Einstein condensate. And that's billionths of a degree above absolute zero, but in a system that's operating at room temperature.
So if I get you correctly, like the fact that you get the atoms in your quantum objects to be cold without the need for cryogenic system and auxiliary refrigerator, this is like a huge advantage for your type of technology, right?
Yeah, it's a huge advantage for a number of reasons. And so maybe the most straightforward reason is the colder you can make your atoms, the more stable they become. So the way that time is kept around the world, the way time is kept with GPS, for example. So when you're navigating with GPS, or the way time is kept for trading networks is using something called the cesium atomic clock. It's the world's timekeeping standard. And that basically relies on the frequency of vibration between two energy states in the cesium atom. And that's the same atom and the same energy states we use in the quantum computer. So they're very, very stable. The other advantage is one of scale. So really for quantum computers to be able to do truly useful work, to discover new drugs or to be able to solve logistics problems in ways that have never been possible with classical computers, will require tens of thousands, hundreds of thousands, maybe even a million qubits. In the glass cell that I showed you this, I'm holding up here, we could actually fit tens of thousands of qubits. These are individual atoms that we pack very, very close together. Some of the other approaches, Google has shown a graphic of their kind of vision of what a million qubit computer looks like. And it's literally the size of a basketball court, right? So if you wanted to take a quantum computer and put it in a data center, let's say, or put it on a satellite, there's no way to do that with something the size of a basketball court. So ultimately our goal longer term is to move these devices to the edge, to be able to deploy them in a rack mountable format. And the fact that we're using atoms really enables that.
So I would like you to maybe touch a little bit about how it affects, like those advantages, how they affect the business model for ColdQuanta, because you mentioned Google, and we know that there are other players in the market which try to leverage their size, the relative size at the moment, and their already existing cloud capabilities and cloud access. So their vision is probably most likely that they will hold the computers on their sites, and you can buy your access and compute time. Some others will probably do some like hybrid in between. They will hold some in their premise, and most of your time probably will do cloud. Do you aim for like a computer for everyone? Because if it's that small and you don't need all those additional systems in order to keep it cool and operate at room temperature. So basically, everyone can have one, right?
So let me take a step back because you asked about business model. So really, the strategy, if you will, for ColdQuanta is we're a quantum platform company, and really the only quantum platform company in the industry. There are others that do quantum computing of one flavor or another. There are some that manufacture components for the quantum ecosystem. There are others that do clocks or sensors. And really, at the heart of what we do, this technology for trapping atoms, cooling atoms, manipulating atoms, underlies everything we do. So in terms of kind of core competence around ultra-high vacuum technology, around photonics, atomics, and software, that is really where we're building a real depth of world-class IP, and that enables all of these different use cases. And these use cases kind of reinforce each other. So innovations that we may do with the quantum computer, for example, will inform what we're doing in the sensors area, and so on and so forth. Then back to your question of quantum computing, yes, I think today, and certainly near term, these will be very large devices that sit in the provider's data centers. So for example, our quantum computer is in a room about 20 feet behind me here, and it's about the size overall of a small room today. And it requires very precise HVAC and temperature control and environmental control. And these things are essentially going from being science experiments to now becoming commercial companies, commercial systems. If you think longer term, though, you'll need to have a quantum computer very close to the classical computer, because a lot of the applications that run are hybrid applications. So think of machine learning, for example. There have been demonstration of machine learning applications that take part of the problem and hand it off to a quantum computer, but the rest of the problem is handled classically. And then the same thing is true, for example, there's a very well-known algorithm for looking at molecular ground state energy, which is very important when you're trying to do chemical simulations. And that requires a classical component and a quantum component. So ultimately, as these things scale up, to get the most benefit, you're going to need to have the quantum computer and the classical computer very close together. There's another example. There's a lot of interest right now at the intersection of sensing and computing. So taking quantum data from a quantum sensor and then processing that data on a quantum computer without destroying the quantum state of the information. That also requires the quantum computer to be deployable to the edge. So there's a lot of reasons why, to really unlock the value of these devices, that edge deployment will ultimately become important. And again, atoms lend themselves very well to that kind of modality.
So you touched on this use case of satellites, and it's something that I heard you mention previously. So I get it that now when we want to deploy something in space and we want to shoot it up, it needs to be as light as possible, as small as possible. And you show this small glass chamber, definitely smaller than what we see in like the usual pictures of superconducting qubits. So I get it why it makes like perfect sense to use them. But once they're up, what exactly can we do with them? Like, why should we want to have a quantum computer on a satellite?
You mean it's not enough that it's just super cool to have a quantum computer on a satellite?
Besides
that, so we actually have a quantum system that's on the International Space Station operating right now. So it's one of our systems for creating Bose-Einstein condensate. And we did this project in collaboration with NASA. We've actually done 2 of them. I think we may be working on a 3rd. So these were systems that were originally kind of a square meter or so in size, what's called an optical bench, which is what the physicists used for constructing these systems, that we then miniaturized down to the point where it was kind of the size of a small dorm refrigerator, and it was put in the SpaceX rocket and launched to the ISS. So it has to be extremely robust to vibration, to shock, to the G-forces, so on and so forth. And the reason for that system operating in space, that was more of a scientific experiment where in low gravity, there's certain kind of characteristics of these Bose-Einstein condensates that you can look at that you simply can't do under regular gravitational field. The reason for a quantum computer, one of the kind of side effects of the atomic approach that we take to quantum computing is these atoms can actually act as very good quantum memories. So you can take quantum information, you can capture that quantum information in an atomic array and hold it for reasonably long periods of time. And so to build ultimately the quantum internet, we're going to need these quantum memories. And it turns out for a variety of reasons, if you look at these quantum key distribution networks, for example, that space is the best place to be putting these repeater nodes. And so it won't be a 1,000,000 qubit quantum computer on a satellite, at least I don't see the rationale for that, although, never say never, but really kind of smaller quantum computers, atomic-based quantum computers that can operate on a satellite as a node in a network to really enable this concept of the quantum internet.
And who do you think will be eventually the users for this quantum internet? Like, what are the advantages that they will gain from that over the already established normal or classical internet that we have?
Yeah, so I think, look, the reality is, despite what you may read in the media, it's still very early and it's uncertain as to kind of really how these use cases will play out. There's two in particular. One of them is if you want to network quantum computers together, you need to do that while maintaining quantum state. And the way you do that is through a quantum communication network. So that's certainly one aspect of it. There is another aspect where there's been some early work done looking at how you might network together quantum clocks for more accurate timekeeping on a global basis. That also requires a quantum network for that synchronization. And then the one that's probably the most kind of covered in the media is this concept of the quantum key distribution network. So the idea that you can have a network where if somebody is eavesdropping on that network, it destroys the quantum state of the information and you instantly know that you've been compromised. And there's certainly a lot of interest there kind of from a national security standpoint, certainly for anyone who's dealing with a high degree of security or regulation around data. But that's still very much at the early use case demonstration, right? China's demonstrated, I think, some pretty interesting results with 1,000 kilometer or 2,000 kilometer through fiber optic cables. There's a couple of examples in the UK with British Telecom and Toshiba that just stood up. So we're still in the early days of demonstrating the technology.
Yeah. But definitely, like, if I get you correctly, the ability to know that you've been compromised, it's a key feature for this type of communication, right? So
right.
Everything from government and military and stuff, it's kind of obvious that they would like to use it, but also I think like other type of like financial information or other stuff that you want to really to keep close. This is something that can also benefit from such stuff.
Yeah, I mean, the issue is, there's a couple of issues, and I'm by no means an expert on quantum communication. One issue is when you think about security, you always have to think about what's the weakest link in the chain, right? So you can have two nodes of a quantum network that are connected together, but those two nodes ultimately need to terminate into a classical network. And so if somebody can infiltrate that classical end of the communication, then regardless of the fact that your quantum information may not have been compromised, you still may have been compromised somewhere in the delivery chain. And that's why the NSA has actually come out publicly and said that they're not intending to use quantum communication networks, partially for that reason, and also partially because from a kind of a national security standpoint, they have to be able to be communicating in fairly rugged environments, and QKD is still a pretty fragile technology.
I got you. Actually, it's kind of surprising that they are kind of out saying that they want to use it, but like you said, we never say never, right?
Never say never. Well, maybe they're saying they won't because they actually are. I mean, who knows? That's certainly the public information that's out there.
I got you. And there may be two stuff that you mentioned before. The first, that you're actually kind of a quantum platform company. So you deal not just with quantum computer, but with also quantum sensors. And you mentioned the experiment that you're doing on the ISS. Right. So can you tell us a little bit like what type of sensors or what type of information is actually valuable to get via those type of devices, and what advantage we derive from it?
Yeah, sure. You've probably seen in the news with what's happening in Ukraine right now that Russia's been taking out large amounts of the GPS coverage in that area, right? Because if you're a soldier or you're driving a tank or you have a drone, right, all of these require GPS connectivity, right? That's certainly from a military standpoint, and certainly from a consumer standpoint as well. If you think about your self-driving car, for example, it requires a number of technologies, but principally GPS to know where it is. But GPS can be spoofed, it can be denied, it can be hacked. So there is a significant amount of work, certainly that we're doing on what we call quantum positioning systems. So this is the idea that once you know a point of reference, a starting point, if you can measure acceleration, rotation, and time very accurately, then you can by dead reckoning know exactly where you are on the face of the Earth to very, very high precision. And it turns out that these atoms are also exceedingly good for that kind of application, because atoms obviously are very sensitive to inertial forces, to rotation forces, acceleration forces. And so we have developed technologies, quantum accelerometers, quantum gyroscopes, obviously highly sensitive and precise clocks. And we have a number of government programs underway that are investing behind the development and then ultimately the commercialization of these technologies. The other side of it, maybe slightly further out, is what we call quantum RF sensing. So I mentioned before, we're using these cesium atoms, and the way that we entangle the cesium atoms is we excite the outer electron of the atom to a very high quantum state. But that high quantum state is very sensitive to RF radiation. So we actually shield the quantum computer from the outside world. Well, you can use that high sensitive to RF to create an extremely sensitive antenna, 100 to 1,000 times more sensitive than anything that's possible classically. So there's some really interesting applications there, again, from a obviously from a national security military perspective, but also in terms of just more commercial use cases. So we're talking to a number of telecom providers and folks in that industry about how we might replace the enormous kind of antenna farms that you see for cell phone communication for 5G and 6G and beyond, with literally a cell that would be a cubic centimeter and controlled by lasers. And then your ISS question, yeah, the reason for the ISS, so the system we put up on the space station creates this Bose-Einstein condensate, and in free fall, in microgravity, you're able to get much colder temperatures. I think it gets down to the pico-Kelvin region, which is like a trillionth of a degree above absolute zero. So it lets them study fundamental physics in a way that's just not possible on the Earth.
Crazy.
Kind of mind-blowing stuff.
Yeah, exactly. It's like, if you think about like outer space is like about 2 degrees Kelvin, and you're like
3, yeah. So there's a slide I like to show in presentations, which is, you know, if you ask the average person, where's the coldest place in the universe, they say, well, it's outer space, right? So outer space is, as you rightly say, is 3 Kelvin. And then the superconducting folks are operating in millikelvin, so 1,000 times colder. Our quantum computers, microkelvin, another 1,000 times colder. And the Bose-Einstein condensate's nanokelvin, another 1,000 times colder. So, you know, it's, again, when you think about what that actually means, it's really, really quite profound.
Very nice. So I want maybe to shift gear a little bit and maybe talk specifically. We can talk generally about the industry, but we can maybe focus on ColdQuanta as an example. We know that there are a lot of technical and engineering kind of difficulties because it's a new technology, it's new stuff, it's extremely sensitive, and we're still getting the hang of all those kind of stuff. But besides those kind of maybe obvious things, are there any other challenges that as a company in this new market you need to face or deal with? Like maybe, I don't know, getting the right people or getting fundings or venture capital that need to get into this kind of business, or government regulation that inhibits part of your work or stuff like that.
Yeah, so I would say, so funding's not been a problem. We're actually very well funded as a company. There's a ton of money, as I think you know, flowing into quantum, both from venture and from government. In fact, government funding has really exploded in quantum around the world, largely, I think, as a response to what's happening in China. I think the number one challenge for us, and it's not just for us, it's for anyone in the quantum industry, is people. So if you think about, I came out of the software world. So the US creates something like 65,000 new computer science grads every year. The US creates about 2,000 physics PhDs a year, and of those, how many of them have? There could be all kinds of physics, right? But so the kind of physics that's relevant for our business, maybe there's a few hundred, 500 a year. So in the software industry, we used to talk about the war for talent and the challenge in hiring. It is nothing compared to the challenge of hiring in the quantum industry. So I think that's certainly one. And then certainly regulation today, there's certain parts of what we do, like in the quantum RF side, that are what's called ITAR controlled, so International Treaty on Arms Regulation. But generally, quantum computing is not export controlled. And so there is an ongoing discussion that the industry is having with government to say, look, you want to tread lightly here, because if you over-regulate the quantum computing industry, you're going to stymie our ability to innovate and to partner and to sell, and you'll ultimately put the US at a competitive disadvantage. And so that is certainly, I wouldn't say that we view that as a near-term threat, but that's certainly a risk of government kind of over-regulating and ending up, destroying the industry before it really gets started.
And before we move to the question on the chat, maybe on the same note, what are the types of skills or capabilities that the folks here on the series can actually contribute? So, coming from a business background, some of us also are engineers, some come from different perspectives, but what do you think we can provide and help to bring progress to this type of industry?
Yeah, look, I think in general, to borrow a phrase from Jeff Bezos, it's day one in the quantum industry. IBM, who's had quantum the longest, has had quantum computers for 6 years. It's nothing, right? And if you think back to the start of the classical computer industry, in the 1950s, so 6 years is nothing. And I think we're kind of still at that point where these things are coming out of the lab and becoming really commercial. So I think there is a ton of opportunity for folks like yourselves coming out of MBA programs, and whether your kind of interest and focus is in business development track, product management, marketing, finance, there's going to be opportunities across this industry because the industry needs it, right? Most of these companies are still run by physicists. I mean, if you look at whether it's when the ones that are public, IonQ or Rigetti, or many of our competitors, they're run by scientists, and those scientists desperately need, in most cases, to bring disciplined business talent to the table to help them turn kind of a cool science experiment into a real business. I will say, for those of you who have engineering backgrounds, obviously that's always valuable to be able to understand, not obviously to necessarily understand how the physics works of of a quantum computer, but to have that understanding of how technology is developed and the challenges of building and scaling and competing in the technology market. But I will say equally well, it's not necessarily a prerequisite, because there's so much work that has to be done in building this industry, or even in kind of going into the venture industry. You know, there's a number of funds now that are specializing in deep tech, or that have deep tech teams that are focusing on investing in this area. And I think those opportunities will continue for many, many years to come.
Thank you very much. So let's open the chat, and the first one to ask was Kishan. So maybe you would like to go and ask yourself the question.
Yeah. So, do you want me to just answer the question, Kishan? I see it here in the chat, or you can go ahead and ask it, whatever you prefer.
No, why don't we save some time? I just wanted to ask you about your funding and your revenue structure at the moment.
Yeah, so you're correct. Last round of funding was last year. Revenue structure today, we're a private company, so we don't share the revenue publicly. I think we have shared information about revenue growth, which has been very substantial. Large part of that revenue is still government revenue, just as a function of kind of where quantum is in its development. And I expect that to shift far more to commercial over the next kind of year to 2 years. We haven't yet publicly released our quantum computer. That's happening here very shortly. So most of our revenue today is in this kind of sensing and components and quantum products area. So hopefully that answers the question.
Thank you. And
then Austin, your question. Yeah, so we do, Fran Fleisch, Sue Gordon, we have a couple of ex-CIA agents on staff here in various functions. We do have actually a couple of people, I think, who were ex-NSA or NRO. So there is a strong connection to both government and to the intelligence communities. In terms of demand from the IC, I think certainly in the sensing area, I mean, this is going to be a major area of interest. So again, if you think about the positioning for the military to be able to operate satellites, drones, submarines, rockets, soldiers, to be able to deploy and do that in a way where they're not reliant on GPS is a huge need from a government perspective today. And then certainly in terms of the RF sensing, to be able to increase the sensitivity of RF detection, the breadth, the bandwidth of RF detection, and to be able to do that with literally 2 to 3 orders of magnitude increased precision and increased bandwidth scope, RF direction finding, for example, being able to determine that there's a signal, where the signal is coming from, in these huge areas of interest. And then just in generally in quantum computing overall, you know, you'll read about quantum computers are going to break RSA. That's many, many years off in the future. But there are many applications of quantum, certainly in the logistics area, in the combinatorial optimization area, where there will be applications from an intelligence perspective, in the machine learning area as well, much nearer term.
Great, thank you, Paul.
Any other questions? Yeah.
Just come off mute a moment. Yeah. Hey, Paul, thanks. Great chat. Full disclosure, I'm joining one of your competitors going to IBM this summer. So
very good.
Looking forward to learning more about this industry. One thing I'm always curious about to get for people who know is in your mind quantum going to be able to break blockchain technologies, or is there a way to kind of use quantum computers to create a quantum proof blockchain, if you will?
Yeah, I mean, this goes to, so there's a couple of things there. So there's this kind of broad question of when will quantum break cryptographic technologies, right? And whether that's for blockchain or just RSA encryption for internet traffic. And that will happen. There's a famous algorithm called Shor's algorithm, which demonstrates how you can basically factor very large numbers. And that's really at the heart of much of cryptography. You know, will that happen next year? Absolutely not. Will it happen in 5 years? Possibly. Will it happen in 10 years? Yeah, quite likely. So the issue is not so much kind of from a blockchain perspective, and I'm not really a blockchain expert. The concern there is more, again, if you think about from a national security standpoint, or even financial information, privacy information, there's the fear of what's called collect today, decrypt tomorrow, harvest today, decrypt tomorrow. So in other words, if I can steal information, if that information still has value a decade from now, great, I can just wait until the quantum computers are ready, and then I've got my key and I can decrypt the information. So there's a degree of concern there. There is this concept of what's called post-quantum cryptography, which are algorithms that are being developed that are resistant to decryption by a quantum computer, because they don't rely on just two large prime numbers being multiplied together. And again, I'm not a cryptography expert by any stretch of the imagination. NIST right now is running a contest to determine what they're going to recommend for what's called PQC, post-quantum cryptography. So there is an effort underway to essentially upgrade the internet infrastructure, and certainly for companies to upgrade their encryption. And I believe there are some post-quantum blockchain technologies being investigated as well. Now, that's not to say we may choose a post-quantum cryptographic algorithm, and some super smart mathematician several years from now may determine, well, actually, there is an algorithm for addressing that with quantum computing. But at least as far as the mathematicians believe today, yes, there are approaches that will be resistant to those attacks.
That's great. Thank you. No, super interesting stuff. Thanks for being here.
Pleasure. And I will say, when you go into IBM, we partner with IBM. So the language that you'll program our quantum computer with is Qiskit, which is IBM's
Qiskit,
language. It's open source. And so, I kind of view them, yes, to a certain extent, they're a competitor. They're also a partner of ours. One of their senior execs from the quantum business actually recently left IBM to come to ColdQuanta. And I think very high, what they've done in the education area is really just so super impressive. I mean, that's the way I learned about quantum computing, was using their textbook, doing some of their challenges, the educational materials, and the community they built are second to none.
Cool. I look forward to digging into it this summer. So it's definitely fun. This cool tech for sure.
Absolutely.
So, Paul, you referred to Robert Suter that moved from IBM over to you guys, right? So, do you mind tell us what's the idea behind, like what kind of role he's going to play with you, or is it like?
Yeah, I mean, he's on our website as VP of Corporate Development. I think kind of not corporate development so much in the classic sense of the word, kind of from M&A, but ultimately building partnerships, customer relationships, partner relationships for us. Yeah, I think again, there is a lot of movement between companies in this industry. I will say one of the really kind of gratifying things about this industry, and I think it's kind of so necessary early on in the development of a new industry, is there's a tremendous amount of partnering and collaboration that's happening between companies that you would otherwise think of as competitors. So, for example, the glass cells that we make, we sell to other quantum computing companies. We actually happen to be one of the world leaders in miniaturized trapped ion packages that we sell to quantum computing companies that are using the ion trap methodology. So there's a lot of kind of co-opetition, I guess is the word that's used for, we're competing, but we're also collaborating.
Yeah, people were wondering when will we reach to the end that this collaboration will stop because revenue flows will start to be significant enough to kind of detach those collaborative partnerships. But I guess it will probably take a couple of more years until we'll see.
And I think it will very much depend upon the nature of those relationships, right? So, for example, the quantum algorithm developers and software platform providers, there's a question as to what extent does this industry become vertically integrated, or is there really a place for segmentation and specialized kind of best of breed providers in various layers of the stack. There's other companies that specialize in, the very complex control electronics and control systems. There's an Israeli company called Quantum Machines that are doing really terrific work there. And then on the software side, there's another actually Israeli company that we've partnered with called Classic, doing some really interesting work in kind of simplifying the process of writing quantum algorithms. And actually, I think as the revenue scales, the depth of those partnerships probably intensifies, because ultimately those will be shared customers or increased demand for those services. The collaboration between companies, that remains to be seen, and then and the nature of that collaboration may well shift, right? So we may collaborate, for example, in lobbying the government around regulation. We may collaborate around developing standards or some core underlying technologies. I mean, much of that remains to be seen.
Thank you.
But that's what makes it kind of interesting, as MBA is kind of coming into this space. You can be part of helping to answer those questions.
We hope we will. Any more questions? Anyone? No. Well, if not, then I guess this is it for today. So thank you, Paul, for coming and talking to us. It was like an amazing talk, and thank you very much for shedding light on all those topics. And thank you all guys for joining us, and hope to see you next time.
Great, my pleasure. Very nice talking with you guys.
Yeah. Thank you very much.
Cheers.
Thank you.
Bye-bye.